Good afternoon, everyone. My name is Joel Esposito. I'm from the United States Naval Academy, which is the Navy's undergraduate college. I'm in the Robotics and Control Engineering Department, and I'm going to tell you about some joint work with my colleagues, Svetlana Avramov and Charles Nelson. So, as you might imagine, for the Navy, the idea of secure wireless underwater communication is a really important technology. And while there's existing technologies like acoustic, for example, it's very slow and very loud and not secure. There's also, of course, fiber optic cable, which is very fast, but that's going to make it hard to have this kind of ad hoc network where you might have divers and underwater vehicles and so forth all interacting. So one scheme that was recently proposed to overcome some of those challenges is a scheme where there's a laser. And the laser is capable of generating a very specialized type of beam. And for our purposes, you could just imagine this beam has a wavefront that looks like a symbol. So for example, imagine it's like the letter B. And then we're going to shine this beam onto another surface and take a picture of it and try to figure out what letter, what symbol has been transmitted. Now, one of the challenges is that as the beam travels through this underwater environment, which has temperature gradients and debris in the water and currents and air bubbles and so forth, the image will get distorted. So on the receiving end, the B will no longer look like the original letter B that was transmitted. So Doster and Watnick's idea in 2016 was to try to use a convolutional neural network, which is a specific type of deep learning algorithm, very good at recognizing images, to classify that into the most likely member of the alphabet that it would match. So in this case, a B. So in terms of what this would look like, this is a video of our own experiment. We cycled those beams through 15 different patterns. You could imagine each one could represent a symbol of the alphabet. They don't look like the letter A or B, but we could use them to encode that information. And that beam was shined through the underwater environment with turbulence and scattering and so forth. And here our CNN algorithm tries to classify in real time or decode the most likely match to this image. So you can hear it's matching to these templates what letter this most likely is. Of course, we want to do this fast. Of course, we want to do it robustly. But what we're really going to focus on in this presentation is doing it fast. If you want to recognize or transmit voice calls, if you want to transmit video information, you have to be able to do this quickly. So I'll compare our work to related work and point out some interesting things. So we'll start with the part of the environment that the laser beam travels through. Early work used air as a transmission medium. It's a much more forgiving environment. There's a lot less optical turbulence in air. Later works transmitted the light through water, and that can be more challenging. In terms of the turbulence, though, many of these works use what's called simulated turbulence, which means they don't actually induce turbulence in the environment, but instead they use a special screen that simulates how the light would be diffracted. One thing that's going to be really different about our work is that we're going to have a much more diverse set of experimental conditions. Another interesting thing about related work is they tend to use a small number of images. So some of the early works used on the order of maybe a few hundred images, which by modern machine learning standards is a very, very small data set. Moreover, if you want to establish that algorithm is 99.9% accurate, that's very hard to do in a statistically significant way with such a small data set. So one of our goals is going to be using a much, much larger data set. So our data set that we've compiled is over 165,000 images. It's 20 times larger than the next largest data set. And it involves real beams propagated through true experimental environments, not simulated turbulence. We have 11 different environmental conditions. And I think all the machine learning practitioners in the audience know it's very important to have more data and more diverse data. So we've achieved that with this new data set. That's a significant step up from anything that's been used before. The next thing that I'd like to talk about compared to related work is our architecture of our CNN, the architecture that we use to recognize what the images are. Most of the related works have used what's called transfer learning, which means they use an existing CNN, an existing algorithm, and they retrain or modify it for their application. So early papers used AlexNet at the time. That was very popular. Later ones used other things, including ResNet. We're going to use a custom network. And part of our motivation for that is we conjecture that these other networks are just overkill. They're just too complicated, too computationally intensive for this application. And the reason why we want a simple network is so that we can get a fast decoding rate. So many other works do not even report their classification rate or how quickly they can decode the symbols in the alphabet. And that's fine if you intend to decode them offline. But if you want to have real-time, say, voice or video communication, that won't suffice. So one of our contributions is going to be a network that decodes over 10 times faster than existing networks. Let me say something about how AlexNet and some of those other networks work and why we decided to make our own custom network. So every time I show someone that problem, they say, well, why did you just use AlexNet? And it's a great question. AlexNet was one of the first convolutional neural networks. In a sense, it's what put them on the map. It was used to win the ImageNet competition around 2013. And this paper has been cited over 76,000 times. So it really was a seminal paper in this field. The way that network works is it took in color images because the nature of this competition was to be images from this ImageNet database. So color images, they're larger images, 254 by 254, feeds them through a series of 5 convolutional layers. In these layers, there's over 4 million learnable parameters. So when you train the network, it's learning these 4 million filter coefficients to pick out different features of this original image that might be interesting. The final layer is a dense or fully connected layer called, and this has over 59 million parameters, 59 million weights that you have to learn in training that combine these features and then assign this image to one of 1,000 different classes, things as diverse as a penguin or a tree or a zebra. When you do transfer learning, what you're doing is you're freezing the weights in the first few layers. You're trying to take advantage of the learning that AlexNet has already done by learning all these filter coefficients. But what you're going to change is you're going to make your input images pictures of lasers instead of cars. But you are locked into using that original image size, and you have to force them to be color to match the architecture that's there. Then you're going to replace that output layer, those 1,000 different classes, with our class, which is just 15 different beam types. And you're going to erase some of those connections or reset some of those connections in that final layer. And then you're going to retrain this network, which means you're going to come up with new weights just in the final layer, not in the whole thing, but just in the final layer. Try to take advantage of the learning AlexNet has already done and just customize it to your problem. So what's good about this approach? The good thing is it's much cheaper than creating AlexNet from scratch. You don't need millions of images to do so. Another good thing about it is you're using existing code. So if you don't want to program your own custom network, this is a great approach. What's bad about it? Well, one thing that's bad about it is you're stuck with this input size. So our images don't need to be 256 by 256 color images. That's not necessary for our application. It's probably overkill. We probably also don't need 65 million weights to be able to discern the difference between our images. And in fact, that's going to take us very, very long to execute the classification. It's going to mean that it's not going to be suited for a real-time application. So our approach was to make a much, much smaller network. We've customized the input to be 64 by 64 grayscale images. We've made the convolutional layer much smaller, only 35,000 weights instead of 4 million. And the output layer is only one dense layer and 15 categories, 90,000 weights instead of almost 50,000. So a massive difference in the number of weights. And the number of weights really is the number of multiplications and additions you need to classify an image. So with much fewer weights, you have a much quicker classification process. So we wanted to compare the speed of our network and its accuracy to some existing approaches. We knew AlexNet wasn't a great choice. It's an older network. It's not tuned for real-time applications. So a recent paper by Neary compared several deep learning architectures, and they found that ShuffleNet was a really good lightweight alternative, meaning a smaller network but still performs fairly well. It's still much bigger than our network, almost triple the number of weights, but it is a good alternative. So the main thing that we're concerned about was speed. How quickly can we classify images? And it turns out that with ShuffleNet, we were able to get about 26,000 classifications. I'm sorry, 26 classifications a second. And our network is an order of magnitude faster at 275 hertz. So we're very proud of that. That's a big difference. I'm not even going to show the numbers for AlexNet because it's slow and it's not really suited for that. Of course, speed's our primary concern here, and that's the reason to use this smaller network, but speed's not very important if you're not accurate as well. So we also compare the accuracies. So here's as the number of training images grows, that's what you see on the horizontal axis, the accuracy should increase. And what we see is that for our network and ShuffleNet as well, of course it increases. When the amount of data is small, ShuffleNet does better, and that makes sense because it's leveraging its previous training experience. But our point is that once we have sufficient number of training images, our network may be smaller, but its performance is statistically identical to that of the bigger ShuffleNet. So we're not sacrificing accuracy to get speed, and that's an important point. Maybe another takeaway here that's just interesting is, either network, more images are better. And that's not anything new to the people in the data science and machine learning community, but it seems to have not trickled down to this corner of the literature before because they're using very small data sets. So the takeaway from our study is that more data is better, real data is better, and that we're able to use this custom shallow network for a really fast classification without trading off accuracy. Our future work is that we're going to use a 256 beam alphabet, largest alphabet ever created, using this approach and try to classify it. As you can imagine, that will be even more challenging. We'll turn to that in the future. Thanks so much for your time today. Really appreciate you listening. Have a great afternoon. Look forward to your questions.